Welcome back to Introduction to Computational Fluid Dynamics. I'm Professor Steve Miller. Today we'll talk about the closure problem of turbulence, which leads into our first discussion of particular formulations and turbulence models and their use within CFD. Last time we talked about a basic introduction to turbulence, and we looked at two of the most famous cases of turbulence theory, that is, if it's semi-empirical or analytical and statistical. The first was by Kolmogorov, who, of course, invented the idea of and found the Kolmogorov length scales, which are based only on the estimations from the current dissipation rate in the turbulence and, of course, the viscosity. Using a Reynolds number, we can estimate what the cascade length is, if you will, the number of orders of magnitude in the cascade. This is going to be important in our future work here. And it's critical to understand for resolving turbulence within a CFD simulation. The second case we looked at, of course, is the turbulent boundary layer. In the turbulent boundary layer, we looked at the law of the wall. And of course, we discovered that there's some sort of self-similar collapse, if you will, with a few empirical parameters for most, if not all, turbulent boundary layers. The exact form of these equations is argued in the community. Nonetheless, it can help us estimate the number of grid points we need near the wall to resolve the turbulent boundary layer. This should always go back into your computational grid generation side of things, but you'll also need to choose a correct turbulence model to resolve a particular type of boundary layer or other types of flows. Finally, we classified a few different types of turbulence models, which we'll be talking about in this class. This discussion today is going to lead up into the RANS-based type models mainly. In this class, we'll talk about the idea of closure. That is, how to close the system of equations that results from a type of averaging. The averaging, of course, is the Reynolds averaging, which is about a mean flow and a perturbation quantity. We'll talk about different averaging techniques for these flows and how they're applied. Then we'll derive and show the Reynolds stress equation, which is one of the most important equations for most contemporary turbulence models used in industry and CFD today. Finally, we'll review the scales of turbulence and how this relates to this modeling. Finally, we'll talk about something that most students aren't familiar with, but is critical for benchmarking and creating turbulence models, which is the idea of the two-point correlations and their related scales. Let's look at the topic of closure now. Turbulence will consist of random fluctuations. Now, random, I don't mean in the true sense that they're unpredictable, but they do have some probability and statistics behind them to back them up. Turbulence is scientifically random. It appears random because of the chaotic nature of the equations. Recall our discussion of the butterfly effect and chaos theory. Turbulence is a continuum phenomena, which we defined, and it is deterministic. The most important thing to remember about turbulence for now is that it's a deterministic process, and the statistics of the fluctuations of the field variables appear random, but they are predictable on a statistical basis. For this reason, we use statistical approaches, which are almost always used and generally required to make practical numerical predictions. We will talk about other approaches which do actually find the actual pressure time history and time density, time history, etc., in a later classification in this module, but we will here mainly focus on the statistical prediction of the turbulent quantities. Of course, this is something also useful because we can use it to compare with measurements. Now, the first popular approach was introduced by none other than Reynolds in 1895, amongst other amazing things he did. But here, he examined and expressed all quantities, unknowns that is, in the Navier-Stokes equations as a sum of a mean quantity and a fluctuating quantity. The mean quantity, according to Reynolds, was a time average. That is, he took the flow variables and substituted in the time average plus a perturbation, which of course is just a decomposition. This decomposition contains really no simplifying assumptions by itself. Unfortunately, as you'll see in the mathematical part of this class, you'll see it introduces additional variables. And then, of course, we have more variables and unknowns, which represents the closure problem. In particular, the Reynolds averaging process introduces turbulence stresses throughout the flow field, and these must be modeled. This is very difficult in itself, and is the subject of many people's careers. Now, these additional quantities and their use hopefully will result in the same number of equations, which would result in, of course, the success of the closure problem. Let's continue our closure introduction. First, let's examine, by example, a number of velocity fields. In particular, we'll look at a velocity field of a turbulent boundary layer over a flat plate. Here in the figure on the lower part of the page, the x-axis represents velocity. The y-axis represents the distance from the wall. So y equals 0 is the wall, and a high value of y, of course, is farther away from the wall. And now at one particular position on the wall in the turbulent boundary layer, we have plotted the velocity itself. And so you can see these are not really the straight behaved lines which we showed in the composite profile for a turbulent boundary layer. The composite profile of the turbulent boundary layer, of course, was an averaged value. We use capital U in that part of the class to denote it. These are the exact velocities that were measured in a turbulent boundary layer at particular times, and they're simply overlaid each other. Now, it doesn't mean that the one on the far right is a higher magnitude on the far left. They're just shifted by a little bit to show their differences. You'll see at high values of y, the value u is almost the same. That's because it's an undisturbed medium. Near the wall, there's huge fluctuations of u at any particular times. You'll see that in this flow, they've injected multiple hydrogen bubbles upstream, they convected downstream, and then they trace their outline with after taking their photographs and superimposing them. Now, there are 17 of these profiles, and they all correspond to the same distance of the leading edge. Your major takeaway here is that each one of these is unique, and it's very likely that each one in the future will be unique. It's of course possible to have two that are alike, but for a high turbulence flow, high Reynolds number flow, it's very unlikely. And so we're faced to trying to predict these types of fluctuations. Ideally, we would find their time-dependent behavior, but we can't necessarily predict them and compare them with experiment. For example, if the one on the left was our prediction, and on the one on the right is our experiment, if we overlaid them, they'd be totally different. And we would say that our prediction was wrong. This is one reason why we were inclined to use, of course, statistical approaches. Now, what's one way to handle this problem? This is what Reynolds thought about through the averaging process to find a Reynolds-averaged set of equations. Reynolds introduced an averaging of all quantities from the particular measurements. For example, he would take every particular fluctuation and superimpose them on this particular graph, which is really what was done originally, except they were separated out so we could see them. And he tried to obtain some sort of standard velocity profile from some sort of process. And so you can imagine he would take every one of these instances of u and ensemble or mean average them, and he would find the mean boundary layer profile. Coincidentally, this is what we would find from a measure and simply time averaging each particular component of u individually and superimposing them. It's two different ways to find the averaged or mean boundary layer profile, but it will result in exactly the same result. How wonderful is that? Now, we will consider our flow to be easily decomposed into a mean component, that's time average, and a fluctuating component. And of course, we are very thankful that at the time of Reynolds and before, and of course today, we have very advanced statistical methods to find and analyze this complex behavior through the averaging approach. Let's make some notes about the averaging. Now, there's going to be multiple useful kinds of averages within CFD, and in this class, we'll look at three in particular. The first is the time average, which is we're averaging each particular quantity of interest at a particular point in space over time. Another one might be the spatial average, where we're averaging a value over a particular space. So we would integrate over space versus time to find the average, or sum if you're in the discrete framework. And of course, there's ensemble averages, which we'll explain a little bit more in a second, but it's basically an average over multiple experiments. Essentially, we've performed an ensemble average of this particular set of data to produce this mean boundary layer profile. Nonetheless, the time averaging is the most appropriate for stationary turbulence. That is, the statistics of turbulence are invariant with time. That means that all statistics of the turbulence that we can derive from a flow field that's space and time dependent will not change with time. We call these types of flows statistically stationary or time invariant. A steady laminar flow is also a case, one case which falls into stationary flow, which is time invariant. But we're more interested in, of course, the turbulent case. So we're not really going to consider these techniques for the steady laminar flow. A steady turbulent flow, remember, is an unsteady flow. A steady turbulent flow is an unsteady flow. That's because the fluctuations are actually moving, velocities and pressures and temperatures and other variables. So when we find a steady solution of a turbulent flow, we're also finding the turbulent statistics, which represent the statistics of the fluctuations, like we showed in this previous graph. Now, for example, let's look at the time average in particular. We'll define the time average of a particular quantity as, say, some function f, it's arbitrary for now, of, say, x, at a particular spatial position x, as the limit of capital T goes to infinity of 1 over t of the integral from t to t plus capital T of f of x t dt. You can see this is exactly the definition of an average, in that we're integrating under the curve, essentially, of f over all times, and then we divide by all times. And of course, take the limit as t goes to infinity from one particular starting point, t. You would always select t time to be when this flow is statistically stationary, and a large T for when, of course, it remains statistically stationary. For example, this would not apply if your engine is starting up, if you're looking at engine. You would start this average once the engine has risen to its steady state conditions, as one example in many. This is the particularly dominant technique within the field of CFD, and we'll look at a little bit other techniques for averaging, for example, mass-weighted, when we talk about compressibility effects. There's also spatial averaging, which is very useful for homogeneous flows. And for example, if we have homogeneous turbulence, we might look at a spatial average. This would be nothing but the same type of equation, except we're averaging over time instead of space. The spatial average will, of course, average over space and remove it from the equation. And we would have an average which varies with time over one particular spatial coordinate. We could also average over multiple spatial coordinates, and that's fine too. There's certain times when this is very useful. For example, what if you wanted to know the average density within a volume over time? You could then, of course, just multiply by the volume to find the average mass over time. This could be useful when looking at a plenum, which of course is exhausting to the atmosphere. Let's take a minute to talk about another important average, which is the ensemble average. And the ensemble averaging will be the most general type of Reynolds average, which is suitable for all flows. It's best illustrated through an example. For example, if we have n experiments which are performed and we have some function f, which we're measuring at any space-time, that particular measurement will correspond to f sub n. So for example, if we performed the exact same experiment 10 times, we could set n equals 2, and that would be the measurement f at position x and time t in the particular f experiment. In this case, the second. So we can rewrite the time average and generalize it into the ensemble average. Now, a time average is a generalization, of course, of the ensemble average. F, which is our ensemble average quantity, would be the limit as n goes to infinity, the number of experiments goes to infinity of 1 over n, times the sum over all experiments with that particular measured quantity. So you can imagine, if we start up our wind tunnel and take a measurement in the flow field at time 10 seconds 100 times, we would put those 100 measurements from 100 different wind tunnel tests in the summation. We would then, of course, put n, capital N as 100, and of course, we would remove this limit because, of course, this is a discrete framework. Now, for flows that are both stationary and homogeneous, then all these averages we talked about are equal. Why? First of all, a stationary flow means that it is statistically stationary and time invariant. The statistics are time invariant, not the actual flow itself. Homogeneous means that if we move in different spatial positions, that the statistics don't change. So if our spatial statistics aren't changing and our temporal statistics are not changing, then you can imagine if we take ensemble averages or spatial averages or time averages, they'll all be equal. You can show this mathematically. Now, this assumption itself is known as the so-called ergodic hypothesis. For Reynolds averaging in our class, we will focus primarily on time averaging, which by definition is, of course, what Reynolds averaging is. But there's other types of Reynolds averaging, maybe Favre averaging, which we'll also show later. Now, here's the actual Reynolds average operating on the value or field variable u. We would also apply this to pressure or density, etc. We'll just show it for u. So, In the original equations, we might have the value u sub I at any point x and time t. We will replace it with its time average value, we'll write that as capital U, and the fluctuating value with u prime. So this is the mean or time average value at every point in space, and notice there's no argument of time. It's only dependent on x now. And the fluctuating value will only be dependent on the spatial coordinate and its time. In this equation, x is always the same, right? It always is the spatial coordinate. We wouldn't have it u at one position and u prime at another. That wouldn't make any sense. So you see, all we've done is decompose every variable into its average and its fluctuation. Let's visualize this so this choice makes physical sense. In this particular graph, we have an x-axis, which is time, so time is increasing. On the y-axis, we have u. U is the original velocity variable in the Navier-Stokes equations, as an example. Now, u is illustrated in this graph as the solid line. That's the original value of u, and what we would ideally love to predict. Instead, we'll try and predict the average quantities and the statistical quantities derived from u prime and u. So, capital U is the average, and we've drawn it as a dashed line. So we would take the solid line and find the average over all time capital T. We would then find one value, and notice capital U, the average quantity, is only a function of x. It is not a function of time, so it does not change with increasing time. It's the dashed line, which is not changing. And it shouldn't change with time. It should be a constant, especially for statistically stationary flow. What would u prime be? Well, u prime here would be nothing but u minus the average of u. So you can see u prime, where my cursor is a small positive value, and then goes down with increasing time to negative time, etc. And it fluctuates about the mean value. So if we take the time average of course, u, the fluctuating value, we would find 0 by definition. Now, the time average velocity, which we define now, can be inserted into our general averaging equation. It'd be the time average of u equals the limit of t goes to infinity of t to t plus capital T of u dt. So u is our original value in the Navier-Stokes equations, and now u is the time average. This is done at every grid point within the domain. Now, the time average on the mean velocity is the same time average value. Think about that for a second. For example, if we take the time average value and time average it over any amount of time, it of course should give us the same average. Here we'll denote the notation bar. The over bar on a value represents the average. So of course, if we have an average of say 10 meters per second, and it's time invariant, and we take the average, we would of course retain and obtain 10 again. Averages of averages, which are time invariant, are not going to change. This is what the statement is saying. I've already mentioned that the time averages of the fluctuations are 0. Here's the equation to show it. For example, if we take our decomposition, excuse me, this should be u sub I, not u plus I. So this term here, please correct in your notes, that is u sub I, not u plus I. The original value of the flow minus it's an average, so this is basically inserting the fluctuating component, and then we put in our time average equation, the limit of t goes to infinity, 1 over t of integral t to t plus capital T of dt, will be written and expanded out. Since it's an integral with a subtraction sign, we can do both individually and use our original terms. We'll have an average of an average, which is the second term, that's u bar, and the first term, of course, will be the original definition of the average, which you showed here in this equation, middle equation on slide 9. And I'll go here. And if we subtract the average minus the average, a bar could be here, of course, it will be 0. This shows that the average of a single fluctuating component is 0. So for example, u sub I prime, that's the fluctuating value of the velocity in the x direction, that average would be 0, according to this averaging technique. This rule would change if we use different kinds of averaging that are weighted. Now, if a flow is not statistically stationary, we can have some problems. For example, how might this be used and implemented in this type of flow? Here we have time again. The y-axis is the velocity component, And then we have fluctuations. The solid line, of course, is the fluctuations of the original velocity. And we can find a mean value. This is almost like a short time history mean. So the mean value about this type of the flow here is higher than a later time. And so the mean is changing with time. This means, unfortunately, that the flow is not truly statistically stationary. And that might be okay. We still can actually use this approach. It's a non-stationary statistical flow, and these averaging techniques will work as long as the averaging is slowly varying relative to the fluctuating quantities. You'll see this in practice. We can also use some alternative form of the averaging definitions down here. Here, this one's the same essentially. It's the velocities decomposed into the mean plus the prime. And here's the same mean velocity definition. Now you'll see in these particular flows, which are treated with Reynolds averaging, that the decomposition will be a problem, as the mean and average are of course related. The time average of the product of averaging is non-zero, which is the first equation. This is no longer non-zero for this case shown, where we have a case with an average changing over time. So the time average of the product of the averaging will be non-zero, and this is going to be known and called as the spectral gap problem. This is overcome by a different type of simulations, formally, mathematically, by approaches called large eddy simulation. Now, averaging works on other types of mathematical operations. For example, here we have an average if we have the pressure with the partial derivative in the x direction. So this term here is partial p partial x. Recall your index notation. We take the average operation by running a bar over it. It will just be, of course, the average of pressure partial derivative in the x direction. It works on mixed partial derivatives too. For example, partial u to partial x partial y as an example. Its average would be the partial average partial x, partial y. So these averaging operations work seamlessly on the derivatives in the equations, but of course it's not luck at all, it's a mathematical fact. Averaging is also a linear operation. So if we have a quantity, C1a plus C2b, and a and b are fluctuating quantities, then we'll have C1 capital A plus C2 capital B. So we could perform the average on the whole thing, or separate the averages on the pieces and write them separately. So remember this, the averaging is a linear operation, and we can separate out through summation the individual averages. These will be coming in handy in a few minutes. Finally, averaging unsteady terms in the equations of motion will result in 0 for stationary turbulence. So in your CFD solver, when you select steady, you're essentially saying that the unsteady terms, the averages of the partial derivatives, will amount to 0. This is particularly written out here. Furthermore, there's a linearization which might be useful for the second term of the right-hand side if we expand out this particular time average on u and u prime for a stationary or non-stationary flow, which is what we've written here. This might be written if we neglect u prime as small relative to u. We can say, hey, for a unsteady turbulent flow, which we're doing Reynolds averaging, that average of partial u partial t, for example, will go as partial u partial t. So you see we've dropped the second partial u prime partial t term, because of course we're assuming there's a linearization where u prime is very, very, very small compared to the underlying base flow or mean flow. Though this assumption cannot often be made. For example, in a shear layer, which is a type of flow which we showed earlier in the class, or a turbulent jet where another shear layer exists, or anywhere there's high shear regions and turbulence, this is going to break down. It's an assumption which might be troublesome later. Now, usually we've looked at all these statistical operations on one point or statistics. We've only looked at one point in time or space and took averages. But you might wonder, what is the benefit of taking statistical quantities across 2 points? And this is going to be critical in this field. For example, we're going to up here and have to understand averages or other types of statistical operations on 2 different variables at 2 different points in space and time. These will appear through these statistical approaches, which are critical. Throughout most students' academic careers, they've only been asked to find a statistical quantity at one point in space usually. For example, the average temperature at a point on a bar as it heats or cools. Nonetheless, we might ask you to find two particular quantities. For example, the velocity at one point and the density at another. Here's a general example. We have two quantities, phi and psi, capital values, and we have the following. For example, if we have the actual fluctuating values of phi and psi and we take the average, we would then do a Reynolds decomposition. We would then have the average of the product of phi plus phi prime and psi plus psi prime. We then, of course, expand out the two terms in the averaging operation. We would have the average of phi, average of psi, plus the average of phi times the fluctuating value of psi, plus the average of psi times the fluctuating value of phi, plus the fluctuating values of phi and psi. Now, we can simplify this greatly because, of course, of our original ideas of averages being equal to averages and averages of fluctuations being equal to zero for stationary flows. And so we can rewrite this as, and it's a linear, so we can treat each of these terms on its own according to the linearization definition on slide 11, equation 2, as the first term as the average of phi psi, which are just, of course, themselves, but they're averages of averages, so we remove the bar. And then the second and third term will be zero. Why? Because we can remove in the averaging term phi and psi from the operation in the limit outside the integral, and we're left with an integral over time of psi prime and phi prime. Those will go to zero. Then, of course, our final term will be the average of phi prime psi prime, and we cannot reduce this to any of our rules. So we're left with an average of two fluctuating quantities at two different points in space and time, if you wish, as equal to their summation of the averages of the two quantities, phi and psi, plus the average of their fluctuating quantities. This is an amazing property. We're going to use it because it eliminates 2 and 3 terms in the equations. So the mean of an average quantity is the average quantity, and a fluctuating quantity has zero mean because, of course, the mean of the value is zero. Here I'm summarizing our finding. If the average of phi prime and psi prime is non-zero, then the quantity is correlated, and if zero, they are uncorrelated. I've just introduced a new concept of correlations, which we'll look at it later. But basically, a correlation dictates how much related these two particular quantities are with each other. If this average of these two quantities is zero, then it's uncorrelated. They have nothing to do with each other. That is, they're completely uncorrelated. Their correlation would be zero. We can also look at the same type of quantities, but in triplets. Say we introduce a new variable, zeta. So now we have 3 fluctuating quantities, phi, psi, and zeta. We can expand out and do the same operations, and we'll have phi, psi, zeta, the average quantities, plus the averages of the first 2 fluctuations times the average of the third, plus the average of the second and third fluctuations plus the average of the first times the average of the first, plus the average of the fluctuations of the first and third quantities times the average of the second, plus this triplet average, if you will, phi prime, psi prime, zeta prime, averaged. Very interesting. So you can see the more values we have on an average, the more terms on the right-hand side we have. And this is the simplest form we can put it in without knowing anything more about the structure of phi, psi, and zeta, given the assumption that the flow is statistically stationary. Now, let's use these statistical tools to develop and find the Reynolds-averaged Navier-Stokes equations. Let's follow along with what Reynolds essentially did, but he did it with a simplified form of these equations. Note that we'll look at the steady, incompressible form of the equations in motion. We are not going to consider the unsteady compressible case, which of course we'll do later by reintroducing compressibility effects in a later class. Now our equations, if we assume that they're steady and of course incompressible, will be partial u partial x equals 0, and we've taken rho away from the time derivative. We'll have rho of partial u partial t plus rho of partial x j ui is equal to right-hand side pressure gradient plus the stress terms. And we've already talked about these before, so we won't review them again. But they're basically the viscous terms. Now we're going to use the Reynolds averaging approach. For every one of the unknown variables, u, p, etc., we substitute in our equations the Reynolds decomposition. For example, p will be p bar plus p prime. And we simplify the equations with all the identities and simplifications we just showed in this class in the previous pages. Once you do that, you will find the Reynolds average of these quantities, and you'll see these particular equations. These are essentially a form of the Reynolds-averaged Navier-Stokes equations. That's because the Navier-Stokes equations have been Reynolds averaged. Here's the continuity equation. It's now partial u partial x equals 0. You'll see capital U appears instead of little u. Look at the right-hand side momentum equation between the two terms. Rho partial u partial t, rho partial u partial t. You can see these are exactly, indeed, identical terms, except instead of the original variable, we have the fluctuating variable. The rest of the terms remain the same, except this particular term, the second term. You'll see there's an extra formation of uj prime ui prime bar. So this is the only real extra quantity that appears in the equations, except for the values we're solving for are averages instead of the fluctuating value. So now the power of these equations, and we're able to find the averaged values of velocities and pressures, etc., which is something we can measure in wind tunnels and use for prediction. Except the difficulty, of course, is from this nonlinear term, we have an extra term here. This is called essentially the Reynolds stress term. And this is the major difference in the average equations. It is ui prime uj prime bar, the average of the two velocity fluctuations in the convection term. You can do something similar to other equations, like the energy equation if you're working in the incompressible framework. Now, the fundamental problem of turbulence modeling can now be seen, and it's devising the extra equations to close the system of new equations to compute all the mean flow properties of the flow under consideration. For example, in this second set of equations, the Rand's equations, we have unknown variables of the average of u, p, t, etc. But now we have this extra unknown term, and it's basically treated as an unknown variable, and we need to understand and how to close the system of equation. This is the fundamental problem of turbulence modeling. This is what we call the closure problem. So we can rewrite and try and rewrite the Rand's momentum equation in a different way. We might move that Reynolds stress term here to the right-hand side and group it in, of course, with this partial derivative here. That's a simple operation to do. Here we formally define the Reynolds stress term as negative rho of ui prime uj prime bar. That is the negative of the density times the time average of ui prime uj prime, the fluctuating velocities. And then we put it on the right-hand side as a stress. And so the Rand's momentum equation is very much like the original Navier-Stokes equations. The left-hand side is exactly the same, so is the pressure term, except they're operating on mean quantities. And of course, we still have the same stress term, but operating on mean quantities. And now we have an additional Reynolds stress. And how do we model that? Because we have more terms than equations. We'll note some important properties about this particular equation. And it's specifically, the Reynolds stress tensor can be written with rho removed as a definition, mind you. We'll note that just like the original stress tensor, it is also symmetric. So formally in 3 dimensions, it has 9 components because it's a 3x3 tensor. However, it does have the properties of symmetry, just as discussed in the original Navier-Stokes equations by Navier and Stokes and their contemporaries. Reynolds showed this mathematically too. We can now have an additional 6 unknowns. Since there's 9 components of the Reynolds stress and it's symmetric, you can imagine we only have unknown values along the diagonal and 3 off-diagonal terms in 3 dimensions. In 2 dimensions, we would have 3 additional unknowns. So even though we have a 3x3 tensor essentially, it only has 6 unknowns because it's symmetric. We can just set the off-diagonal terms to be equal to their sister off-diagonal on their side of the diagonal. Now, for steady 3-dimensional flows that are incompressible, we will then have, if you count them up, 10 total unknowns per grid point. You might write them down for yourself. You know that 6 already are the particular components, diagonal and off-diagonal, of the Reynolds stress term. The other ones are the original averaged field variables. So we have 10 unknowns and only, essentially, no new equations. So we have a non-closed set of equations, and we must model these to proceed. This is the idea of turbulence modeling. We need to create or think about new equations to close this model, to have 10 total equations for 10 unknowns per grid point. And this gets more complicated in compressible flows, of course. This is where the idea of the Reynolds stress equation comes in. We need to try and close the RANS equations. And of course, the moments of the Navier-Stokes equations could be used to find additional equations. That is, we take each of the original Navier-Stokes equations or RANS equations and take their moments, and we can form additional equations. Let's think about that for a second. How would we do that? Well, let's look. There'll be multiple Navier-Stokes equations through the fluctuating properties and the time average components. So we can write a differential equation for the Reynolds stress in a tensor form. We'll let an operator, calligraphic math n, we'll just call it n, on u be equal to the right-hand side. You can see this is exactly essentially a differential equation for the Reynolds stress tensor. Look at how these terms appear in, of course, this equation here. We're essentially finding the Reynolds stress tensor term here, isolating it, and writing it as an operator on the other terms in the RANS momentum equation. That's what this equation is here. Take a few seconds to see if you can do this yourself. We'll say that this is the so-called NS operator, where the momentum equation can be written as n of 0. Now, we can average this equation. Let's look at the averaging technique here. If we apply through moments, we might write ui prime of n of uj plus uj prime of n of ui, and it'll equal to 0. Now, let's substitute in, because remember the linear operation of each term in our operator n into these following equations. For example, let's look at the first and second terms, ui prime n uj for rho partial ui partial t. That's what you're seeing right here, rho uj t plus uj prime rho ui t. So this is partial rho ui partial t average. What we're going to do is go term by term through this Reynolds stress tensor with this particular averaging technique of the moments and setting it equal to 0 by definition. And we'll expand these out using all the rules we discussed in this class of averaging of 2 terms or 3 terms and expanding them out and setting terms to 0, which should be 0 because of course averages, fluctuations are 0, etc. We can simplify these. And then we'll go term by term and add them all up to form this original average equation and set it to 0. That's what we'll do here. So we're not going to go through this step by step, but just look at the first one and go from expanding it from left to right. For example, the first step is very simple. We just take this average and split it into 2 parts because of course there's a summation here. So it's a not linearization, but it's a linear expansion. We then examine each particular term on its own through additional expansion because there's sums here. And then we can get rid of 2 particular terms because they're 0. And of course we can combine them because of their likely of how they're written. And then we finally get the final term, negative rho of partial tau ij partial t. Here, tau ij is the original stress tensor. The convection term is written here. You'll see we have rho ui prime uk uj k. So you can see here's the ui prime term, and we're looking at the second term in the operator. We expand those out. So you can see we do this for every term in this expansion. And we get these terms for each particular equation, which I've listed on these pages, pressure gradient term, viscous term, etc. Now, the summation of these terms for the appropriate right-hand side and left-hand side in the equation will result, of course, in this Reynolds stress tensor equation, which is set to 0. And then we move around the terms on the right-hand side and left-hand side and put them in this form. We put them in this form on the bottom of the page for a very good reason. And of course, that reason is that we want to put it in the same type of form as the Navier-Stokes equations, where we have, say, some time derivative plus a convection term will be balanced by pressure gradient terms plus stresses. That's what we've done here in this final Reynolds stress equation, which we just derived. We have some time derivative with the Reynolds stress plus the mean velocity with the partial derivative of the Reynolds stress in space. That's the convection term of Reynolds stress will be equal to the right-hand side. These are very much like the pressure gradient terms. That's why they're placed there, but they're operating on U and the Reynolds stress. And of course, we have all the viscous terms, which are expanded out from, of course, these steps. So we have derived a new equation with no assumptions, simply by taking the moments. And you might think that's a major victory, but oh wait. You'll see if you look in this particular equation that there's certain triplet and averages and also averages over partial derivatives of the velocities, etc., and velocities with pressure. These represent themselves new unknowns. So through this and taking the moments, and because of the symmetry of the stress tensor, we've generated 6 new equations. But unfortunately, we have generated 22 new unknowns, and you can count them up if you look at this equation. For example, the triple correlation term will represent 10 unknowns. If we look at these other terms of velocities and pressures and velocity gradient terms, you'll see they represent 6 and 6. So 10, 6, and 6 is 22. So we have 22 unknowns, which are represented by these operations, but we've only generated 6 equations. So now you might imagine we have a new system of equations, which is only on the order of 10, and we have about 32 total unknowns. You can imagine that we could do additional moments, but no matter how many moments we take, there's more and more unknowns being generated. For example, if we take higher order moments, we'll have even more unknowns. And in fact, there is in fact a mathematical proof which shows that no matter how many moments you take of this set of equations, you'll always generate more and more unknowns. You'll never be able to generate through the moment process, like a Reynolds stress equation example, more equations than, or the equal number of equations than the unknowns. This is very unfortunate and is a proof, it's a mathematical proof which is represented to show the turbulence closure problem. So we haven't closed the problem at all. We still have more unknowns than equations. We can now try and rewrite the stress equation at the lower part of 17 in a new way, and we'll write it here in a compact form. This is the way it will appear more so in literature. You can see it's the exact same equation, but we've just lumped terms in and made some new definitions. For example, we've defined pi sub ij. This will be this particular correlation between p prime and the velocity terms, derivative terms. Epsilon ij will be 2 nu of this particular term, which is very important, and rho cijk will go as the triple correlation plus the 2 direct Kronecker delta functions of 2 double correlations between pressure and velocity. Now, in the turbulence modeling field, these all have particular names. In particular, this is like a production term, and this is like a dissipation term of turbulent kinetic energy. It's like a dissipation. I've already mentioned that if we take higher and higher moments, we generate additional knowns at each level. That's a problem, but still, our goal is to create models of turbulence to close the Reynolds equations. So we're going to have to be very creative and intelligent how we do that. This is the brilliance of this approach and the basis of all traditional and contemporary turbulence modeling. Before we continue, we have to review the scales of turbulence because they're going to be critical for discussing the particular closure of the Reynolds equations. We previously showed in depth the length, velocity, and time scales of Andrei Kolmogorov. Recall that they're called the smallest scales are Kolmogorov scales. They're the smallest scales of turbulence in a flow. The integral scales, similarly, are the largest scales of turbulence in terms of time, length, and velocity over any other particular quantity. They're the largest scales of turbulence. Now, we previously talked about turbulent kinetic energy and how they're related to these particular scales. Go back and look at those equations to remind yourself. Here we can define the turbulence intensity and turbulent kinetic energy, of course, through the particular Reynolds stress definition. This is brilliant because now we're collapsing the idea of Reynolds with, of course, contemporary ideas of Kolmogorov. Now, to do this, we'll have to look at some normalization of the variables with respect to a mean flow because we use Reynolds averaging. Recall, we have values like u prime squared bar, v prime squared bar, and w prime squared bar. Just u prime average itself, by definition of the Reynolds average, is 0. What if we take the fluctuating value of u, square it, and then take the average? This is called the mean square average because, of course, we took the square and then the mean. A root mean square average is the perturbation variable squared, averaged, and then square root. We take the square root often so that we recover the same dimensions. So through this idea and process of the RMS value, root mean square, we can rewrite our velocity statistics in this way, as u hat will be the RMS of the velocity divided by, say, the average velocity magnitude. V and w will likely be the same. There'll be v prime and w prime instead of u prime. And so now we have 3 RMS components which are normalized by the mean values. Let's keep these 3 equations in mind. you can see the beauty of this approach. If we can somehow connect the RMS values, non-dimensionalized, with, say, an experiment. Now, an experiment was conducted on a flat plate boundary layer of thickness delta. Here, the x-axis is y over delta. Delta is the boundary layer thickness at one point in the plate. The y-axis represents the RMS values of u, v, and w normalized by the magnitude of the velocity. In this case, the magnitude of velocity is chosen to be the velocity at the edge of the boundary layer, where y equals delta. Points here are experiments, and the lines are CFD. This is shown in outer coordinates. This is technically the edge of the boundary layer, but you'll see that the turbulence actually extends beyond the edge of the formal boundary layer, where, of course, u bar is equal to the ambient velocity, right at 1. That's a very interesting finding. So what does that mean? It means that turbulence exists outside the mean flow of the boundary layer. Nonetheless, by using this approach and plotting data, we can collapse these types of graphs and figures. And you'll see this is one particular RANS-based prediction technique. So we need to get our RANS equations closed to be able to predict these types of quantities directly or indirectly so they can be compared directly with experiments. Now, you'll also notice here that the turbulence is anisotropic and inhomogeneous. What does that mean? Remember, homogeneous turbulence is where the statistics do not change as you change spatial position. Isotropic turbulence is where the statistics do not change with rotation at particular points in space. So if turbulence is non-homogeneous or inhomogeneous, then the statistics change in space. You can see that by increasing the y-coordinate. The statistics of turbulence are changing. For example, the RMS of u normalized is going down. If it was homogeneous turbulence, it would just be a constant value. The turbulence is anisotropic. Why? Because if we rotate at a single point from, say, the x direction to the y and z direction, the values of u prime do not become v prime and w prime. If it was isotropic turbulence and we make a 90-degree rotation or any type of rotation, the RMS value of course, the new coordinate system would be same as the old one. You can see this is impossible in this particular case, so we call this turbulence anisotropic. Therefore, we have to be very careful when applying the ideas of Kolmogorov to, say, a turbulent boundary layer flow or any type of flow where there's inhomogeneities or anisotropy. Thankfully, turbulence itself generally returns to isotropic regime over time as a so-called memory. This is a beautiful theory in itself. Now, let's try to define the turbulent kinetic energy like we discussed in the previous class. If we take the mean square velocities and sum their components and multiply by 1/2, we'll define the turbulent kinetic energy. This can be rewritten in a simple way as 1/2 of bar ui prime ui prime. That's brilliant because, of course, you can see where I'm going with this. It's going to be the trace of the Reynolds stress. This will be called the kinetic energy of the turbulent fluctuations per unit mass, turbulent kinetic energy. Now, the majority of turbulence models will not distinguish between any particular individual Reynolds stresses, but only between the model and try and model turbulent kinetic energy. We will look at particular Reynolds stress models. So traditional models of turbulence, especially for RANS closures, simply try and find K, turbulent kinetic energy. They do not particularly look for off-diagonal terms. That is to say, there are models that look explicitly for each Reynolds stress term. They're, of course, called Reynolds stress models, and we'll talk about those too later in the class, but more briefly. Now, if our turbulence is isotropic, you can look at this particular equation and simplify it, and you'll find that for a particular isotropic flow, you'll get an exact and beautiful analytical equation. It'll be 100 of the square root of 2/3 of the turbulent kinetic energy divided by the base velocity squared, which of course is constant at the particular grid point. And that will be, of course, the turbulence intensity. Before we get to the closure models themselves in the following classes, we have to set a little bit more groundwork. Remember, thus far we have primarily looked at single point quantities. For example, turbulent kinetic energy is a single point quantity. ui prime will be at a single point. Both these values of u are at a single point x and time t. So here what this means is and this is index notation, mind you, it's expanded to form this part of the equation, they're equal. We might also have to consider, for closure purposes, to close these systems of equations, the idea of finding statistics at multiple points. We have noted that turbulence and the associated flow structures are very large. This means, and you've seen earlier, that we have the idea of correlations through averaging. We would like to know something about the properties of the turbulence beyond one-point statistics, that is, using two-point statistics. Let's review the writing of Townsend, who was a very famous turbulence researcher and fluid dynamics. And this will give you a better idea of where we're going. He wrote, "Unlike the molecular motion of gases, the motion at any point in a turbulent flow affects the motion at any other distant point through the pressure field, and an adequate description cannot be obtained by considering only the mean values associated with the fluid particles. This might be put by saying that the turbulent motion is less random and more organized than molecular motion, and to describe the organization of the flow requires mean values of the fluctuation of the flow variables for two or more particles at two or more positions." And look at that last key statement here. Two or more particles at two or more positions to understand the organization of the flow. This is why we're going to start looking at statistics using the same operations and generalize them at 2 points in space and time. This will let us and allow us to try and close our turbulence models. Let's try and do this through, of course, our terms that we've already developed in the context of our theory of Reynolds averaging and closure. So, first, we will assume that the spatial and temporal separations are related by this particular term. This is a very difficult concept for many new students to get their heads around, but recall the properties of partial derivatives. Now, we'll say that partial of some operator will be the negative mean velocity with the partial with respect to x. What will this assumption mean? It means that fluctuations are convected at the mean flow speed u. So if there's some fluctuations in the flow, they're being convected through the flow at a speed u. This is the meaning of the convection velocity of the flow. That information, that is, the disturbances, are moved along at velocity u. The turbulence is being convected by the underlying base velocity. This is a theory which is part of the Reynolds decomposition. Now, Taylor's hypothesis, who is another famous researcher in turbulence and fluids, is valid, this is the Taylor hypothesis, if the fluctuations are sufficiently weak or small to induce significant changes in the rate of convection or of the base flow. So this equation will remain true as long as the fluctuations are not changing the base flow or mean flow at a significant rate. Taylor's hypothesis. Let's now consider the first correlation of the velocities at one point at two different times. We call these operations autocorrelations. Now, recall the Reynolds stress. We do indeed have off-diagonal terms. For example, I equals 1 and j equals 2. Here, we write ui prime, uj prime. The arguments are x for both terms. That means they're at the same position. And we have time t and t plus t prime. So what we're going to do is say t is the time and t prime is a second time. So in one position, we have two times. This is the definition of the autocorrelation if we take, of course, the correlation of these two quantities, the averaged operation. So autocorrelations are the correlation of two quantities at one point in space over time. These have certain statistical properties which are very valuable, especially in the measurement of turbulence. And they were experimentally examined much well before the theoreticians started to get into them. It represents the time average of the fluctuating quantities at some point in space, but at two different times. Now recall our definition of turbulent kinetic energy is the half the trace of Rij at t prime 0. For example, if we take t prime equals 0 and put it in this equation and set I equal to j, then by definition, the left-hand side will be Rii or Rjj, it's your choice because we're summing from 1 to 3, at one particular position from time t to t prime. Here t prime is 0 because t equals t prime. So we can rewrite this and recover through the idea of the autocorrelation of the turbulent kinetic energy. That's K. So when you're running your CFD codes with a RANS model, it's going to give you K, which is essentially the trace of the 1/2 of the Reynolds stress term, which is, of course, the autocorrelation of the trace terms themselves individually added up. For example, we'll have the autocorrelation of U11 plus autocorrelation of U22 plus autocorrelation of U33. That's why we write RII here. Turbulent kinetic energy at any point in space at time t. So you can see this is written for a temporally evolving flow too. Now, recall in our discussion of Kolmogorov and boundary layers, we found integral scales in terms of time and space. So we have a temporal integral scale. We can recover the integral scale in time from the definition of the autocorrelation in turbulent kinetic energy. You see it's all connected. Here's our definition here. We'll say an integral time scale at any position x in the flow field at any time t will be the integral of the autocorrelation, RII, divided by twice the turbulent kinetic energy. And you'll see, of course, these have units of time. So we have selected these to have the correct units. Remember, K has the units, turbulent kinetic energy, of meters squared per second squared. What should the units of the autocorrelation be of the velocity terms? Think about that. Remember, this is essentially written as an integral. It should have the same units, of course, because we're integrating with time. So that would add, of course, multiply through the units of time. And so we'd recover this. So the integrand is non-dimensional. We've non-dimensionalized the autocorrelation term to get units of time. This represents a characteristic time, or some people call the largest scales of turbulence in time. So by looking at the autocorrelation of the velocity stress terms in Reynolds stress, we can recover the time scale. This is a very important property of the closure problem. Now, for stationary turbulence, we can always simplify this a bit more. For example, if we look at the streamwise component of this Reynolds stress term, we can find u prime of u prime at x and t plus t prime. This is exactly the definition of here, except for looking at the u component only, the R11 component, which is uu. Now, if we normalize this with respect to the mean square fluctuating velocity, we find the so-called Eulerian time correlation, named after none other than Leonhard Euler. Here he appears again. We can substitute this form into our more general form, which we showed up here. The upper part is just, of course, the definition of RII. There are certain properties of this equation, just by definition. For example, say we put t prime equals 0. You can simplify this equation and it will become 1. So by definition, the autocorrelation of, say, a velocity fluctuation or any particular quantity, if it's an autocorrelation where we're setting t prime to 0 and doing the integration in the top of the page, we will find a value of 1. So at higher values of t prime, say they're very, very, very large as t prime goes to infinity, by definition, the autocorrelation will go to 0. Autocorrelations, by definition, for these types of flows are going to be even functions with t prime. So we can let t prime go to negative infinity and again recover 0. If we let t prime go to some finite time, like 10 seconds or negative 10 seconds, of course, they're going to be equal to each other, the value of the autocorrelation, because it's an even function in time. Let us look and illustrate this concept physically. For example, say we have some generic autocorrelation R sub e. Let's look at this particular figure. The x-axis is time. The y-axis is the autocorrelation. If we set the time to 0, by definition it will be 1 where my cursor is. If we increase or decrease time, of course, it will go to 0 for large times. This is all seen through this integral operation here. If we have relatively uncorrelated fluctuations, that is, the time scale of the turbulence is small, then it'll have a very small decay, tau sub e. If it's a very long length or long-lasting or long-living turbulent eddy, the autocorrelation would be very large and the whole width of the envelope would widen out. You also see that typically in experiments and in this illustration, there's actually positive and negative loops as it oscillates down to time equals 0. This is very much often seen in most experimental measurements of turbulence. This is why you can't represent these functions as, say, Gaussians empirically. Now, looking at this, we might imagine that there's some type of scale, which is important for turbulence modeling, that exists between the small scale and large scales, that is the Kolmogorov scale and the integral scales of turbulence. We call these microscales. And microscales can easily be calculated, which are dependent on the time correlation for small times t prime in this range. We'll define a new scale, the Taylor microscale, which is a particular time which is larger than the Kolmogorov scale and much less the integral scale. So, an expansion of the Taylor series of Re, this equation, about time t prime equals 0 will yield this particular equation. So it's just a Taylor series of expansion of the last equation on 24, which of course is the autocorrelation for one component of the Reynolds stress. And we'll find 1 plus t prime squared over 2, etc., partial derivative of Re partial t squared at time prime equals 0 plus higher order terms. Well, if you look at this and simplify it, you'll find 1 minus t prime over ta e squared. You'll note that we've truncated a higher order term, so we can only account for the terms which make this dashed line on the autocorrelation curve. You'll see that the dashed line meets this particular time, and that particular time where it goes to the 0 of Re is the Taylor microscale time. This can be derived and shown analytically now by solving for ta e in the particular equation for Re with truncated terms from the Taylor series. The Taylor microscale term will then be written, as shown on the bottom of the page, as the square root of -2 of the partial derivative of the autocorrelation of the first component of the Reynolds stress tensor with respect to time evaluated at time prime equals 0. So all we have to do is find the second derivative with respect to time of the graph of the autocorrelation, where my cursor is. And take -2 and divide it by that value, take the square root, and we will be guaranteed, of course, to find a positive value for ta e. Why is it positive? Of course, because this is the maximum value of the curve by definition, where it's 1. And it must, of course, be less than 1 to the left and right of the 0 axis. You can show that through a mathematical proof if you're curious. Now, we've shown one-point statistics to find a very important time scale called the Taylor microscale. We need to still go towards our closure problem, which is the whole subject of all kinds of different turbulence models, which are implemented in CFD codes and what you're actually evaluating in this class and others. Let's now consider a two-point correlation of velocities. So once again, we have our two-point correlation. It is now defined as arguments at some position x, some time t, and a new vector r. The right-hand side is very much like before, but here we are setting the first velocity fluctuation or variable or argument in the two-point correlation at position x. The second argument, uj prime, will now have x plus r. This is the original vector x to one position plus another position in the flow, r. So this is a vector addition. They're both defined at the same time t. So instead of doing the correlation over two different times and integrating, we're going to do it over two different spatial positions and two different variables. This is called the famous two-point cross correlation, and it is, of course, a tensor in this case. Here, r is the displacement vector between the 2 points. Compare this equation with the one for the autocorrelations in time. Of course, you can have a single cross correlation if you use two different spatial positions and time. It's a general two-point cross correlation. For example, we could have x and t and x plus r and t plus t prime. Now, once again, if we take the trace of the two-point velocity correlation, we once again get, happily, the turbulent kinetic energy at a point x and t. That is if we take the trace of Rij, once again, and set time to 0. Amazing. Through the integration and normalization of the two-point velocity correlation, instead of finding a time like in the autocorrelation approach, we can find a length scale. So a length scale, the integral length scale of our flow, can now formally be defined through the two-point spatial cross correlation of velocity. And this is its definition here. We'll say the integral length scale L at any position x and time t will go as 3/16 of the integral from 0 to infinity of our 2-point cross correlation along its trace or diagonal divided by turbulent kinetic energy for dimensional considerations. And now we integrate over the vector r essentially. So there's a vector r from x to the new position, perhaps it's y. We integrate from x to y over an infinite distance. Of course, we don't do this in practice because we can't evaluate an infinite distance numerically. But in practice, we can just go to a very large value because, of course, by definition and statistically, because of the statistics of turbulence, we'll never find this value going to infinity over large distances. This integral will result, of course, in a length scale. That's the integral scale of turbulence, the largest scale of turbulence. And so now we've defined a time scale and length scale for integral scales. Now, if we consider a longitudinal correlation function, just like we did in time, we can find almost the same quantity. We'll call that f, for instance. That'll be the first component divided by the RMS of u prime. We can once again define a Taylor microscale, but this time it's a Taylor length scale through the exact same process as we did with the time scale. We would find the second derivative of f in this case using the 2-point correlation instead of the autocorrelation. Put a -2 in the numerator and take the square root. And now we have found another scale of turbulence, which is called the Taylor microscale. Now the Taylor microscale, through Taylor's hypothesis, which we defined earlier, will relate the micro time scale, Taylor microscale, tau, to the Taylor length scale. Lambda will be equal to the flow velocity, the average flow velocity of that position times, of course, the Taylor microscale time. Check if that equation is dimensionally correct. U might be meters per second, and time is seconds. Meters per second times seconds will be, of course, meters, which is the Taylor length scale. Now, if we have an isotropic homogeneous turbulence, we might find a simplified equation using this approach. And this could be seen as a first form of a type of closure. We've related now the turbulent kinetic energy, the time rate of it, will go as the negative of course, its dissipation, as we derived and showed in a previous class. Using this definition, it will go as -10 of the viscosity times turbulent kinetic energy divided by the Taylor length scale squared. That is a simple equation. Now, this lambda can also be related with the Kolmogorov length scale for homogeneous isotropic turbulence through the so-called dissipation rate. Remember, dk dt will go as the negative dissipation. And we can solve for dissipation using Taylor's hypothesis in microscales, as the dissipation will be 10 times the viscosity times turbulent kinetic energy over, of course, the length scale squared, which of course is equal to the left-hand side. So we've done this. We've actually made some sort of early turbulence closure. Though it's all theoretical, it is useful for the development of turbulence models in CFD. Interesting. For very large Reynolds number flows, Taylor argued that the dissipation will go as the turbulent kinetic energy to the 3/2 over L. You can make these same dimensional arguments which are outlined in books on Introduction to Turbulence. We won't go through the arguments here, but let's look at their implication, which are used in many different types of turbulence models. This Taylor hypothesis here is valid for many of the RANS codes we're going to be looking at in this class, and it makes sense. Look at the dimensionality of the equation. Turbulent kinetic energy has dimensions of meters squared per second squared. If we raise it to the 3/2 power and divide by dimensions of meters, we'll get a dimension of meters squared per second cubed. Try it yourself. Now, if we indeed look at these measurements, we can look at these relations and assume that there's particular coefficients in front of them. And if we look at measurements, we can try and find the particular coefficients, because of course this is an approximate equation. We can try and see how they go. And you'll find, through particular measurements of high Reynolds number homogeneous isotropic turbulence, that the dissipation in this equation will go as 0.09 times k to the 3/2 over L. So we found this coefficient by an empirical approach from, of course, experimental measurement. The same coefficient is used to convert between different types of turbulence models, which we'll be discussing in the next few classes. Here we can solve for turbulent kinetic energy, also in this equation, in another form. Now, we can go further and use Kolmogorov's theory, and we can write that the Kolmogorov length scale, recall, as we showed in the previous class, goes as the viscosity cubed divided by the dissipation 1/4. Making this substitution, we can relate the Taylor microscale models with, of course, the integral and Kolmogorov length scales. Let's look at this in particular. So the ratio of the Taylor microscale with the Kolmogorov length scale will go as 7 times 1/3 of the integral length scale of turbulence divided by the Kolmogorov scale. This is valid for all high Reynolds number isotropic homogeneous turbulence, but it's a wonderful and beautiful mathematical result. We'll be using some of these theories to calibrate and create our turbulence models in the next classes. Now, Taylor microscales will initially lie and usually lie always in the inertial range of turbulence. If you look at the graph of the energy spectra with wave number, you'll see that Taylor microscale lies in the inertial range, where of course Kolmogorov's theory is valid. And it lies in a range where the smallest eddy sizes are dictated by the 1941 theory of Kolmogorov. It's important to understand these concepts in the coming classes. A few more points. Typically, the Taylor microscale will have little use in turbulence modeling itself, but it has great impact in theoretical work. And if your CFD code doesn't recover these results for certain types of initial conditions, like homogeneous isotropic turbulence, then it's likely has bugs in it and it has a bad implementation. It does give insight into separating the so-called inertial scales from the smallest eddies at the Kolmogorov scale. So from the Taylor microscale through the Kolmogorov scales, they might be viewed as the smallest eddies. This is going to be critical for a particular type of turbulence modeling, which is large eddy simulation. It might also be seen as a hybrid length scale. Now, it's interesting to note that in this particular function of nu, turbulent kinetic energy, and dissipation, it'll all appear in one particular equations. This is absolutely beautiful. Also, similarly, you can form a similar equation for the Taylor microscale, which has limited practical use in turbulence modeling itself, but it's important to know it's derived. If you go to a conference where they're talking about CFD and turbulence modeling development, they will talk about Taylor microscale a lot because of its very important physical meaning in dividing the smaller scales from, of course, the small scales of Kolmogorov. In this class, we have defined the average operations, and we use them to make the Reynolds decomposition, which we put into the Navier-Stokes equations. We then took the Reynolds stress tensor and showed that and defined the closure problem, that no matter how many moments of the new equations, the RANS equations we take, the number of unknowns will grow faster than the number of equations being formed. This is the closure problem. That means we need to develop new types of equations which are not dependent on the original Navier-Stokes equations, essentially, or derivatives or something of them, to close the model. This is the subject of turbulence models, and people have been working on these concepts for well over 150 years easily. Next time in the class, we are going to look at particular closures from very famous people all the way to models which are used today. The first set of models will be algebraic. Then we'll talk about the so-called mixing length hypothesis model, and we'll find formulations of the first turbulence models for boundary layer equations in theory. That's why we introduced the boundary layer equations in the beginning of the class. Then we'll talk about two famous boundary layer turbulent model closures, the Sibecki-Smith model and the Baldwin-Lomax model, and we'll look at their applications and their advantages and disadvantages for boundary layer flows and separated flows, and we'll discuss their range of applications. So for the next few classes, we're going to take the RANS equations and the fundamental theories of turbulence from boundary layers and isotropic turbulence that's homogeneous, and the length scales and averaging properties and statistical techniques, and apply them all seamlessly to create these particular turbulence models. And then, of course, we're going to look at the implications. We'll do this for the next couple days. Remember, in your CFD solvers, you'll be able to choose these models, and you'll have to know the equations being solved, their assumptions, and what type of flows they're valid for. It's easy to make a bad choice. Thank you very much for your time today. I'm Professor Steve Miller.